Hi class, welcome back to our lectures on electrodynamics. And again, our reference is Introduction to Electrodynamics by David J. Griffiths. And this book is highly recommended for you. So to continue with our lectures, we now then go to multipole expansion. So at large distances or very far away from a charge, you would look like, you would look at the charge to be very small. And when you are far away, the distance between the charge and yourself would be very large. And so your potential or your electric field measured at that distance is very small. And if it's not just a point charge, if it's a distribution of charge, a big distribution of charge with total charge Q, when you are far away, very, very far away, that distribution of charge will look like a point charge with charge Q. Here. But what if the distribution of charge will have a total charge of 0, this one? Of course, you can say that the potential could be approximately 0, but there is something that we should go or that we should look for, like the details of the configuration of the charge. Let's take this example, for example. For this example, we have a physical electric dipole. A dipole consists of two equal charges, one positive and the other one is negative, so they add up to 0. So when you go far away from that, the total charge is 0, but the electric field, supposedly for a point charge, the electric field should go this way, like that, radially outward, when you're far away, when this is a point charge. But the dipole would not have the electric field that's drawn here in the red pen. So let R minus be the distance from negative Q to the point in space, and then R plus be the distance from positive Q to the point P, and this is an angle theta here. This one is 180 minus theta. Okay, this is 180 minus 180 theta on that side. So if you calculate the electric field here, this would just be equal to 1 over 4 pi epsilon Q over R plus minus, for this one, Q over R minus. So from cosine law, let's look at this. R square plus is just R square plus D over 2. This is D over 2. This is D over 2, because the total distance here is D. This is for R plus, this is minus RD cosine theta, and for r minus, this is plus rd cosine theta, or you can rewrite it in this way, this equivalent expression. So if your r is very large compared to the distance here, so if you're very far away, suppose here your r is very far away, then d will be very much less than r, and d would be very much less than r, and this one would be approximately equal to 0, so that you're left with this one here, or this one. If you expand this with the exponent negative 1/2, this is just equal to this one. So therefore, your 1 over r plus minus 1 over r minus is approximately equal to d r square cosine theta. And hence you have your v from this one will have the form of this one here. So what is the feature of this equation? Very far away, you have, if you're near to this charge, if you're very near to this charge, you see two charges, right? But when you go far away, you only see a configuration which has a sum of 0, a charge sum of 0. But look at here, there is a Q that exists in this potential, and the D is also there, the distance between the two charges. So you have 1 over 4 pi Q times D cosine theta over r square. There's nothing similar to V is equal to 0 at very large distance. So you have a completely different view of a charge distribution with total charge equal to 0 at large distance from the configuration. So, and by the way, if you have only one charge, V R would just look like 1 over 4 pi epsilon sub O Q over R at large distance. But of course, if this R is so large, then this would approximately go to 0. This one, of course, this is you're looking at a dipole very far away. Here you're looking at only a single charge far away. So take note of that. So here, evidently the potential of a dipole goes like 1 over r square at large R. And it falls off more rapidly than the potential of a point charge. It's different for a point charge. So at a very, very, very large distance, of course, this will go to 0 more rapidly than for a potential of a point charge. So incidentally, if a pair of equal opposite dipoles are put together to make a quadrupole, the potential goes like 1 over r cubed. For back-to-back quadruples or an octupole, it goes like 1 over 4. So here, for a simple point charge, for a dipole, for a quadrupole, and for an octupole, you have that. And for the next configuration, it will go, it will, the potential would have to be proportional to 1 over r to the fifth. So how many charges would have to be in that configuration? For example, if we follow this one, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, maybe this is 2 to the 4. So there will be 16 charges. So anyway, if the configuration is like that, then we have a different approximation at large distances. So we now develop a systematic expansion of the potential at large distances. So for this figure, you have the potential to be 1 over 4 pi epsilon 1 over r here, rho r prime d tau prime. So using cosine law in this figure, we have r square, the scripted r, will just be equal to r squared plus r prime square minus 2r r prime cosine theta. So you can factor out the r square, and then you have this one. So in this case, you can rewrite this as 1, you can write the scripted r to be r times square root of 1 over epsilon, where epsilon here is just equal to this expression. So for points that are outside a charge distribution, the epsilon is very much less than 1, and this invites a binomial expansion to this expression. So your 1 over r becomes 1 over r times 1 plus epsilon to the negative 1/2. And so this one, epsilon is very small, so you can expand it to be like that. And if you substitute back this one to the epsilons, you will see that this expression is just this one here. And if you look at this, you have 1, and then you have cosine theta, 3 cosine square theta prime minus 1, and this one you also have 5 cosine cube theta prime. These are just the Legendre polynomials. And you can actually rewrite r into this form with the Legendre polynomial here. So let's erase this so that you can clearly see it. So let me erase this one. so that you could see it clearly. And I'll go through the slides very slowly. So that's it. And this one, so I have explained these slides already. Then by the way, the process of approximating this one is also one way of generating the Legendre polynomials. So if you continue this series, you will still find out a lot of Legendre polynomials. So then you can write 1 over r to be the integral of 1 over r times d tau, rho r prime d tau prime. So you can rewrite the potential to be this form, where the r 1 over scripted r would be just this part here. That is the 1 over scripted r. So you can expand this. So here you have the first expansion. This is the second, or the first expansion, the second expansion, the third expansion, and so on. So you notice here is 1 over r squared, and 1 over r cubed. That is the multiple expansion. And so this one is for the dipole, this one is for the monopole, this one is for the dipole, and this one is for the quadrupole, and so on. So here's a problem here which you can solve on your free time. A sphere of radius r centered at the origin carries charge density, this one here, where k is a constant and r theta are the usual spherical coordinates. Find the approximate potential for points on the z-axis far from the sphere. So let's look at the monopole and dipole terms. The monopole term is this one. And of course, this is what we had studied in chapter 2, for example. This is the correct form when Q is at the origin. If the point charge is located in the origin, that is the exact potential. So the r square, the dipole, the quadrupole, the octupole, very far away, they will vanish because they fall off much faster than this. Now, if you have a total charge of 0, the total charge is 0, then the dominant term in the potential will be the dipole. This one, the second term here. This the dipole. This is the second term because that dominates for the dipole because the total charge would be 0. So this one here would be 0. But this one will not be 0. Why? Because there is an approximation for the dipole which we can see, which we have seen earlier. So this is the dipole, and r prime cosine theta prime will just be equal to this one, and so we can write this as this expression. Just replace this with this one, and we can define dipole moment to be this one here. This. And therefore we can rewrite the dipole to be dipole potential to be this expression, just substituting a formula. And the dipole moment is determined by the size, shape, and density of the charge distribution. So we can calculate P. We will calculate P later, or you can calculate P as this one here. And P is just actually equal to, if you do this, QR prime plus minus QR prime minus, this would just be QD here in this figure. So that's it for that. And then there is a question: is this consistent with the physical dipole in example 3.107? That's I think in the first video for this chapter, and no, the second, I guess the second one. So this is consistent with that example, the approximation. Farther and farther away, V dip becomes a better and better approximation since the higher terms die off more rapidly with increasing R. By the same argument, at a fixed R, the dipole approximation improves by shrinking the separation D. So it's the same thing as you go far away from the dipole, or you stay at the same place and just shrink the D. It's the same approximation is the same. And it should be noted that D, the distance between the two charges, should be small enough compared to R in order for the approximation to be safely applied to the problem. So here's a note: if you have two dipoles P1 and P2, the total dipole moment is then equal to P1 plus P2 here. So in quadruple, you have two dipoles. You have here a dipole, that one, and also you can also say that this, you can also say this, that one, and this one. The dipole, the total dipole moment then is obviously for these configurations is equal to 0. This is now quadruple actually. So these are some problems of which you can solve. So let's just for you to screenshot the problems. Origin of coordinates and multiple expansion. By the way, when you have, as I've said earlier, when you have a single charge at the origin and very far away, you have an exact monopole. But if you disturb the charge, if you put that away from the origin, or a distance, or you shift that from the origin, then the monopole would not be the exact one. You have to subtract the distance from the original position to the new position of the charge. So that's what it says here. By the way, the monopole moment, the dipole moment was QD. The monopole moment is just equal to Q. So here, if you have Q in this place, originally Q should be in the approximation. Q should be here, but if you move Q, then your monopole would have to be your monopole used this as 1 over R, but now the monopole would have to use this scripted R. For a dipole, if you change location, if you want to go to another point, which is distance A from the original positions that you had, then the dipole moment would change, and the new dipole moment would just be equal to this one. You can follow the steps here. So you have to change this in the this one would have to change. This one would have to change for here. That's now different. That's now P bar, which is P minus Q times A, where A is the displacement. But for the monopole would have, so if you change the location of Q, then this one is not anymore R, but you have to do the scripted R. That is the distance between the charge and the point where you are measuring the potential. Now, this is the dipole moment for so anyway, if the total charge of a configuration is Q, then you have this. But if the total charge is negative Q, then if the total charge is equal to 0, then P bar will just be equal to P. So these are some of the problems that you can solve in your free time. The problem for that one, I hope you have taken a screenshot. And then electric field of a dipole. So looking at this, you have the potential of the dipole. This is just Rp, and Rp is just equal to P cosine theta over that one, 4 pi epsilon sub O R squared. And if you get the differential of V with respect to R, with respect to theta, and with respect to phi, you will get the corresponding electric field in the direction specified. So this one is for ER, for E theta, and E phi. And if you add them, that's just the electric field of the dipole. And so this is your electric field. So this is not ordinarily radial. You have a theta direction, because if it's just radial, then the electric field would be just this one, radially outward from the distribution. But since you have a theta component, then your field would look like this, or like that. Let me just expand this one. Look, you are very far away from the dipole. You experience a field that is different from a radial direction for a dipole. This one is when, this is for a pure dipole, this one. Pure dipole, you're very far away. This one is physical, is a physical dipole. When you go nearer to a dipole, this is what it looks like. They're similar. It looks similar, but in this one, you have very close charges, and in this one you have you're quite near to the dipole. But if you go far away, for this, if you go far away, then it would look like this. But if you also put the charges very close, if you put the charges very close, it will look like this. It's either you go far away from the dipole and see this kind of field, or you put the two charges close to each other and see this dipole, this approximation of the dipole electric field. So that's it for this chapter. By the way, the one thing that you have to really point out is that R should be greater than D. And so these are the problems that you can get a screenshot. But before that, let's just focus on this last slide and also in this slide so that you can read. And then these are the problems that you can solve. Just screenshot them. I will be posting the assessment for these lectures, for this week's lecture, on our Google Classroom and our Molly Classroom. So that's the final slide. So this is all for this chapter, and the next videos, the next video sessions will be on the next chapter. So watch out for that, and I hope that you've learned something. You don't have to really understand fully, but at least the gist or the general idea should be already in your brain, because when you go to advanced physics in master's or in PhD, you will remember, you have to use the ideas that you have already in your brain to be applied on more complicated problems. But anyway, you still have another course of electrodynamics in the next semester. So for the next video, we will be doing dielectrics, the field inside a dielectric, or what happens to the field if it passes through a dielectric. So all of those things we will study about in the next class. So that's all for today. That's all for this session, and hope to see you next time in the next one.